Okay, in this video we will continue on chapter 4.2, which is on overall heat transfer coefficient and Fouling factor. Okay, now let's see the objective of this subchapter. Okay, firstly, students should be able to determine the overall heat transfer coefficient for a heat exchanger. Okay, second, students should be able to determine the relation between thermal resistance and overall heat transfer coefficient. Okay, lastly, students should be able to develop an awareness of falling on surfaces. So, all these three objectives I will explain in detail at the next slide. Okay, first we will cover on the overall heat transfer coefficient. So basically, a heat exchanger typically involves two flowing fluids separated by a solid wall. So normally this fluid is flowing through a pipeline. So pipeline is in cylindrical shape. So basically, for the heat exchanger, heat is transferred from the hot fluid to the wall by convection. Okay, because a hot fluid is a moving fluid, so we consider the heat mechanism in here is convection. So after this fluid is flowing through a pipeline, right? So the pipeline is a solid pipeline. The material is a solid pipeline. So that solid the heat mechanism occurred at the solid area is through the wall by conduction. So from the pipeline wall to the cold fluid, the heat transfer is by convection. Basically, it is quite similar as compared to what I'm cover inside chapter 2, the thermal resistance for the cylindrical pipeline. Okay, so for this heat exchanger case, the thermal resistance network consists of two convection and one conduction. So basically, this is the figure for the pipeline inside the heat exchanger. So basically, we have a hot fluid inside here. The pink color one is a hot fluid. And then we have it's separated by the solid wall, which is pipeline. So at the outside of the wall, we have a cold fluid here. So we have another pipeline, solid wall here. So basically, the thermal resistance network for this pipeline is starting with the hot fluid inside here is by convection. So you can see here, this first resistance is Ri, which is convection. Then we have a wall, which is our pipeline, this pipeline. So this heat transfer is by conduction. So we have another pipe which is cold fluid here. So because we in the heat exchanger, we consider the heat is being transferred from the hot fluid to cold fluid. So we only consider the heat from here to the wall and to the cold fluid. So there is a 3 medium there, inside there. Okay, for a double pipe heat exchanger, the thermal resistance of the tube wall, we can use this formula. Okay, remember in the chapter 2, I already derived the resistance of the cylindrical tube. So basically, you can refer back to that slide and on how you can obtain this formula. Okay, for this double pipe heat exchanger, to calculate the total thermal resistance, we need to consider like what we see inside the previous slide. We have Ri for convection inside. we have R wall, and we have a RO for convection outside. So each of these convection part inside and outside have different area and also different heat transfer coefficient. So when one fluid flow inside a circular tube and the other outside of it, we have A inside is pi d inside diameter and length. So for outside we have the other outside diameter. So basically you can see from this figure, for inside inner tube, the diameter is at the hot fluid part. Okay. Meanwhile, for the outside convection, for the cold fluid, we need to consider the diameter of this hot fluid plus with the pipeline thickness here and here. So basically, outside is from this point to this point. So please remember this one is a surface area. Okay, now move to next slide. So basically for this heat exchanger, it is convenient for us to combine all the thermal resistance in the path of the heat flow from the hot fluid to cold into a single resistance. So remember in the chapter 2, we have Q equal to delta T over R, right? So basically this Q is equal to UA delta T. Okay, we have a few. So UIAI delta T is for inner. So UO AO delta T is outer. So this one is for the wall. So basically this U is the overall heat transfer coefficient with the unit watts per meter square times degree Celsius. So let's rearrange these equations in order to get the thermal resistance. So what we can see here, delta T is present inside all the equation, so we can cancel out. So after cancelling it out, we can rearrange R is equal to 1 over UA for the wall, UA for the inner part of the pipeline, and UO and AO. So basically we know that for this one is for the inner part convections. So basically it is the same like this. But this one is the single resistance formula. But if we use a U, basically it's a overall thermal resistance. Okay, now we move to the next slides. So basically, for your information, when the wall thickness of the tube is small and the thermal conductivity K is high, so we can say that R wall is equal to 0 KY. Let's have a look to its formula. So basically, if the upper part for the thermal resistance for conduction is thickness, right? So if this thickness is small, sorry, and this K is high, so imagine that if the value for this one is 0.1 over like 1 million, then if we divide it, we can get around 0.000 approximate to 0. So we can say that R wall is equal to 0. So basically we can say that the inner and outer surface of the tube are almost identical because the thickness is very small, right? So AI and AO and also AS is identical. So from the equation previous, we can simplify by cancel out the area because all the area is the same. So we can have this equation 11.5. So we have 1 over U is approximately equal to 1 over HI and also plus 1 over H naught. So we have a few conditions here. If HI is greater than HO, we can say that 1 over U is equal to 1 over H naught. Why? We try to do. If let's say here is 1 over HI around maybe like 100,000. So if we divided it, HI, this part will become approximately equal to 0, right? So that's why we can say that if HI is greater as compared to H naught, we only consider 1 over U is equal to 1 over H naught. So the other case is HI is less than H naught. In other words, H naught is greater. So seems like this condition, if H naught is greater here, maybe this H naught is around 100,000 K, and then if we divided 1 with this value, it will become approximately 0. So we can cancel it out, and what is left is 1 over HI. Okay, so now we move to Fouling factor. So basically this is the figure of the fouling inside the heat exchanger. So basically the Fouling factor cause the performance of heat exchanger usually deteriorates with time as a result of accumulation of deposit on heat transfer surface. So basically this is the figure of accumulation of deposits on the heat transfer surface on the heat exchanger. So the layer of these deposits represent additional resistance to heat transfer and cause the rate of heat transfer in a heat exchanger to decrease. When the resistance increase, the heat transfer rate will be decreased, right? So this Fouling factor can be represented as RF. So this RF is the net effect of this accumulation on heat transfer. So the two common type of fouling is, one is precipitation of solid deposit in a fluid on the heat transfer surface. Maybe the fluid that flow inside the pipeline in the heat exchanger is contaminated, so it will left the solids, the contaminant inside that pipeline and cause the contamination to precipitate. So the other common type of fouling is corrosion and chemical fouling. Okay, in order to account the effect of fouling on both inner and outer surface of the tube, we need to modify the overall heat transfer coefficient formula just now. Just now we only consider the resistance for convection, conduction, and convection inside, convection outside, and conduction, right? So by take into account the effect of fouling, we need to add up the resistance of fouling inside the overall heat transfer coefficient formula. So for an unfinned shell and tube heat exchanger, the formula for the resistance can be expressed as as shown in the formula 11.8. So this one is a convection inner that we have before, and then we have to consider the falling for the inner tube. This is the conduction, our wall, and this is the falling for outside tube, and we have a convection. So for the what is the modification that we do is, this one is a common, this one is a basic one that we need to calculate inside the tube, inside the thermal resistance inside the tube, right? These three. So we just modify by add up the falling factor for inner part and also falling factor for outer part. So this calculation, the consideration of falling factor is very crucial inside the heat exchanger in order to know the performance, the efficiency of the heat transfer equipment itself. So I will explain in detail the example of each of the objective that we want to cover. So basically we have a falling factor just now, we have a thermal resistance, and also overall heat transfer. So I will cover all the example in the next video. Thank you.